Welcome to this episode of Mr. Lehman's Knowledge Explosion. In Unit 6, Lesson 5, we're going to talk about polygons and coordinates and how we determine what a quadrilateral is. So as a reminder, at the start of page 27, we have the three formulas that we've talked about this year: the distance formula, the midpoint formula, and the slope formula. And I've given you in the middle column what those formulas are, in case you've forgotten. But what I'm most interested in is the third column that says, what can I use it to do? And I filled this in for you. So if you're going to use the distance formula, that's good for finding congruent lengths. And if you're finding congruent lengths, you can show parallelograms, or if something's a rhombus or a square, or if the diagonals are congruent, etc. So distance is going to be one of the main ones I use a lot. The midpoint formula would be useful for finding midpoints, and if you have a midpoint, that would mean things like diagonals are bisecting, or maybe I'm going to draw from a midpoint to a midpoint, drawing a mid-segment, and I could use the midpoint formula to help me find those points. The second most important one, though, would be slope, because slope is going to tell me if I have parallel lines. And remember, parallel slopes are going to be equal. And slopes can also tell me if something's perpendicular, because if the slopes are negative reciprocals, then I know they're perpendicular and they have right angles. And again, if I can show right angles, I might be able to show a rectangle or a square. If I can show parallel, then I can show a parallelogram, etc., etc. So those are the formulas we're going to be using. So let me show an example number one, how we go about doing that. It says, is triangle ABC scalene, isosceles, or equilateral? Well, and I know the definitions of those three words are: scalene means all three sides are different, isosceles means two sides are the same, and equilateral means all three sides are the same. So if I'm trying to find out that the lengths of those sides are the same or not, my plan is to find the distance of all three sides and then compare those side lengths. So I've listed AB, BC, and AC is what I'm going to find, and I'm going to do the distance formula in a way that is where I just sketch it from point to point. So I'm going to draw up from point A over to point B, and I'm simply going to count those numbers. So from A of 1 up to 4 was a distance of 3, and from 0 to 4 was a distance of 4. By doing that, I can simply say that AB is the square root of 3 squared plus 4 squared, which is 9 plus 16, which is the square root of 25, which is equal to 5. Now, when I just count up and say it's a distance of 3 and a distance of 4, you need to understand that that's the same thing as when I say x2 minus x1 and y2 minus y1. But I think that's the easiest way to sketch these things. So let's go back and let's find the distance of B to C. Again, I'm going to sketch over and down, and then I look at the numbers. If I'm going from 4 to 7, that's a distance of 3. If I'm going from 4 down to 0, that's a distance of 4. So I can tell right now that BC is going to be 5 because it's the exact same numbers that I used to find AB. 3 squared plus 4 squared, which is equal to the square root of 9 plus 16, which is 25, which square roots to 5. So as of right now, I know that it's at least isosceles. But I can't stop, because if the third side ends up being 5, then I have to say equilateral. So there's no shortcut here. You have to find each of the measurements and then compare them. Now, just looking at AC, it doesn't look like that's going to be the same, but again, I use the same strategy of sketching down and sketching over. So that appears to be going down 1 unit, and from 0 over to, from 0 over to 7 would be a distance of 7. So that means my total distance is going to be the square root of that 1 squared plus 7 squared, which is equal to the square root of 1 plus 49, which is equal to the square root of 50, which we do need to reduce would be 5 square root of 2. So these are my three side lengths, 5, 5, and 5 root 2. And since only two of the numbers are the same, these two right here, I can say that this is, without a doubt, an isosceles triangle. Now, what some of you may be tempted to do is just to look at it and say, oh yeah, AB and BC look the same, so I'll just write isosceles. That's only worth 1 point of this type of problem on a test. I'm interested in how can you verify and guarantee me that it's isosceles. So to do that, I need to see all three of these distances so that I can compare.